Hi everyone, it's Mr. Wolfe here, and I'm going to be going over the second part of Unit 3, really focusing on Newton's second law. And so we're going to be going through targets 1 through 3 again. So the idea of we're going to first look at and draw our free body diagram. From our free body diagram, we could find the net force, and from the net force, we could see how that object is going to change its motion, how it's going to accelerate. So we've done this before with the quiz you guys just took, but now we're going to be looking at motion instead of the vertical direction in the horizontal direction. And so one force that we haven't explicitly talked about yet in this unit, and a very important one, is going to be the force of friction. And so the force of friction is going to happen anytime you have an object moving and it's on a surface. The fact that those two surfaces are rubbing up against each other, that force of friction is essentially going to go against that intended motion. So even if we're on an ice rink, something with very little friction, you're still going to have enough friction where that hockey puck is going to eventually come to a stop because of friction. And so our definition of friction is a force that resists that intended motion of the object. And you could have friction if your object is at rest too. So let's say like we have a refrigerator right here, all right? And let's say you're pushing it with an applied force, right? The intended motion is to move this way, but because of friction right here, it's not going to move. So we could still have that force of friction if our object is at rest. We could also have the force of friction if we have an object moving, let's say like a car, right? And you have an applied force on the car by the engine. But the fact that it's on the road, those tires and the road are going to be rubbing up against each other. You're going to have a force of friction going in the opposite direction of the intended motion. So we've looked at an example of some horizontal forces in this instance, but that doesn't mean that these vertical forces just vanish. So when we draw our free body diagrams, it's not like gravity disappeared. We still have to draw that force of gravity going down on that fridge. And since we have a contact with the surface here, essentially this ground is acting like the molecules in this ground are acting like tiny springs pushing up. That's the normal force going up right here. Same thing with our car. We have our normal force and our force of gravity. All right, so when we draw our free body diagrams, we want all the forces acting on our object. But when it comes to solving for our net force, it's really, really important that we keep horizontal and vertical motion separate. So when we're solving for net force, we have to imagine there's a wall. We cannot mix vertical motion with our horizontal forces. We cannot do that. Right, and so before we go on, another force we could have is also the force of tension on an object. And in this case, the only difference is that just the rope could be pushing or pulling, to the left or right. And we would still have our normal force here and our force of gravity here. And let's say we're going across a surface, there's most likely some type of frictional force opposing the motion of who's ever pulling on this object. So now let's look at an example problem for horizontal motion. And for this problem, we're going to be doing everything. We're going to make our free body diagram. From this, we're going to be able to find our net force, and from our net force, we're going to be able to get that acceleration. So it says draw a free body diagram for Matt's car, who has a mass of 1,300 kilograms. And so I'm going to make this a little bit bigger so I could write that mass in there. So 1,300 kilograms. Remember, I only put the mass in the box, and mass is going to be measured in kilograms. And so we have a surface that it's on, and its engine exerts a forward force of 14,500 newtons. That looks like it's going to be an applied force to me by the engine. So I'm going to write positive 14,500 newtons. And there's also that force of friction. Remember, it's always going to be opposing that intended motion. So intended motion is going to be going to the right. Force of friction is going to be going to the left. And that force is going to be negative, because it's going to the left, 9,000 newtons. Now remember, we're looking at horizontal motion, but we can't neglect our other forces, our vertical forces, just for our free body diagram. So we have the force of gravity, and because we're on a surface, we're going to draw that normal force perpendicular to the surface our object is on, the ground. All right. Next it says calculate the net force. And so that's when we get on to target 2 right here, and we're just going to draw our net force equation. All right, so we're going to say our net force is equal to, I'm going to look just at my forces in the horizontal motion. I'm going to start with my forces to the right, just because it makes the math a little bit more easier. All right, so I'm going to say it's going to be my applied force plus my force of gravity. And that's it. I do not want to incorporate my vertical forces into that equation because we have to keep those separate when it comes to the equation. We cannot combine them. All right, and so my net force is going to be equal to my applied force, which is 14,500 newtons, plus my negative 9,000 newtons. And my net force is going to end up being positive 5,500 newtons. All right. The next problem I'm going to have you guys solve. So it's the same type of situation right here, except now it's saying, okay, calculate the acceleration of the car. There's a couple things that we already know. By looking at that in this net force, it's greater than 0. And so we know that because it started at rest, that it's going to be that we're going to be increasing our speed. But to determine that actual acceleration, we need to use our F equals ma equation. And in terms of what force we might use, do we use the force of gravity, force applied, our net force? We have to look at this situation right here. We care about just overall how that object moves. So I would look towards that net force in order to find that acceleration. So let's first decide what equation do we want to do in order to determine the object's overall acceleration. All right, now we know the equation. Now it's just a simple plug and chug. What is this car's acceleration? Now we know our object's acceleration, we could start solving problems from Unit 2. So I want you guys to answer this question. How far will Matt's car travel if it accelerates from rest in 8 seconds? And so what we're looking for is how far, what distance will it travel? All right, thanks for watching, guys. That's all we have for Unit 3, Vertical Forces.